All right, so what we're going to be doing now, or what I'm going to be doing right now, is a Chapter 8 and 9 exam review video. And my goal here is to give you a demonstration of some of the problems. If I did all the problems, it would literally take me like 10 hours to actually demonstrate all of them. Some of them are quite long. But this should at least give you a sense of and help you to review the process for each one of the types of problems. And so that's my goal inside of creating the video. So we'll start out with actually number 2 here. And so number 2 says we've got d squared plus 4d plus 4 times d minus 3y is equal to 0. And then we're given a set of initial conditions. We need 3 initial conditions, 1, 2, and 3, because if you notice, you've got a squared and then you've got the 1, so that means that this is a third order differential equation. Okay? If I rewrite this here as r squared plus 4r plus 4 times r minus 3. So now what I have is my auxiliary polynomial. I set that equal to 0. And then I could see that this is r plus 2 squared times r minus 3, and that equals 0. Okay? So now we've got a repeated root. We've got r equals 2 with a multiplicity of 2. And then I have r equals negative 2 with a multiplicity of 2. And I have r equals 3. So that means that my general solution is going to be y equals c1e to the negative 2x plus c2xe to the negative 2x plus c3e to the 3x. And you can see, what you should be able to see here is that because I've got the repeated root, that's why I'm adding the power of x in there. Don't forget also you have complex roots, so you're going to have to make sure that you understand how to create solutions using complex roots. Take a look at my videos on that. But this is going to set up our general solution. So now, and this is something I wanted to make sure that I demonstrated, now what I need to do is I need to go in and find C1, C2, and C3 using my initial conditions. Okay? So what I'm going to do first is I'm actually going to take the first and second derivative. So y prime is going to end up equaling negative 2c1 e to the negative 2x. And then will be minus 2c2 x e to the negative 2x plus c2 e to the negative 2x plus 3c3 e to the 3x. And that's just me taking the derivative of each one of the terms. Did it one by term by term by term by term using my rules of derivatives. And then I'm going to take y double prime, and that's going to end up being 4c1 e to the negative 2x plus 4c2 x e to the negative 2x minus 2c2 e to the negative 2x minus 2c2 e to the negative 2x plus, and then this is going to be 9c3 e to the 3x. Okay? So now I'm going to come up here. I'm going to now plug in y. So I've got y of 0 is going to equal, and this will be c1, and if I plug in a 0, that's e to the 0, so that's 1, plus, and then c2 zeroed out, plus c3, okay, and because e to the 0 again is just 1, so I got c1 plus c3, that's going to end up equaling 3. And that's my initial condition right here, y of 0 equals 3. Now I'm going to take y prime of 0. First term here is going to end up being negative 2c1. And then we're going to end up with, this is going to zero out. Then I'm going to have plus c2, and then plus 3c3, and that's going to end up equaling 2. And so now we're going to use y double prime of 0. So this is going to end up giving me 4c1. And then this will zero out. And then this will be minus 2c2 minus 2c2 plus 9c3, okay, which is 4c1 minus 4c2 plus 9c3, and that's going to end up equaling negative 2. So now what I have is I have a system here, okay, c1, c2, c3. I can actually do this in any order in terms of the lines that I want. So I'm going to set up my system. I will have 1, 0, 1, 3. And then I'll have negative 2, 1, 3, 2. then I'm going to have 4, -4, 9, -2. I'll go in and use some technology in order to row reduce that. And what I get, my RAF of this, ends up equaling 10057 over 25, 010 22 over 5, 001 18 out of 25. So now I just need to put that back into my original function y. So that means the solution to my initial value problem is going to be y equals 57 over 25 e to the -2x plus 22 over 5 x e to the -2x plus 18 over 25 e to the 3x. And that actually solves, is now the particular solution to this differential equation given those initial conditions. All right? So basically just utilized that auxiliary polynomial in order to find my solutions to actually go out and find my general solution. Right? I have C1, C2, C3 because this is a third order differential equation. Okay? Once I've gone out and actually generated that, then I took the required number of derivatives, right? In this case, it's 2 derivatives because I'm going to need 3 solutions. Basically, just plugged in my values, okay? And then I set up a system, solved the system, and plugged in my variables back in. All right, so I've got y double prime minus 2y prime plus 5y is going to equal 7e to the cosine x plus sine x. So what we're going to be doing now is we're going to be solving a non-homogeneous differential equation. We do have constant coefficients inside of our homogeneous part. And both of these, e to the x cosine x and sine x, are both, we can use our method of undetermined coefficients or annihilators. I'm going to actually, instead of utilizing an annihilator here in this case, I'm going to go in and I'm going to just find my trial solutions given the fact that I know what I have here. Okay, so in order to do that, I'm going to demonstrate that. I'm going to first, I have r squared minus 2r plus 5, okay, is equal to 0 is my auxiliary polynomial. And so I'm going to use the quadratic equation. I'm going to get r equals, it'll be now -2 plus or minus the square root of -2 squared minus 4 times 5 times 1 divided by 2 times 1. So this ends up being 2 plus or minus the square root of -16 over 2. So this is 2 plus or minus 4i over 2. And so that's 1 plus or minus 2i. And that is the solution. So what we have is we have a complex solution here to our polynomial. Okay? So I'm going to write down my solution. I'm going to get y equals, and so remember this is an a plus bi, and so my solution is going to be e to the ax times cosine bx plus I sine bx, and actually we can just drop off the I, so it just becomes the sine bx. So we're going to get c1 e to the e to the 1x, and this will be then cosine 2x plus c2 e to the x, and this is sine 2x. Okay, so that's my my solution. Now, what I have here is I want to now take a look at my non-homogeneous part, 7 e to the x cosine x, and I'm going to make a comparison, and my comparison is going to be to these two solutions. Okay, I'm going to see if I can find a trial solution, and I want to know then, once I found a trial solution, whether or not I can actually utilize whether or not I need to modify it based upon my homogeneous part. Okay, so I look here and I notice that I'm going to split this up. So I actually have 2 of them, and we have a theorem that says that if I have basically a compound non-homogeneous part, I can separate out the 2 parts of the non-homogeneous part and solve each one of them individually. So I'm going to do that. I'm going to start out with 7 e to the x cosine x, and I'm going to note that it is not identical to either one of these homogeneous solutions. given that that's the case, okay, what I have is I then have a set of trial solutions that I can use here, and the easiest one here for me to use is just, this is going to be a naught e to the x cosine x, okay, right, and plus b naught e to the x sine x. So this is the complete complex solution that corresponds to e to the x cosine x. Remember, if you're using a complex trial solution, you have to have both parts, both the sine part and the cosine part. Otherwise, you may not necessarily get the correct solution. Okay, so that's going to be my trial solution. There is, inside of your book, in 8.3, there actually is there's a chart of trial solutions that you can use, kind of handy. And then you just need to make sure that you know how to pick them. Okay, and then, so that's my first one, that's for number 1, and the second one is sine x. Okay, so for sine x, I'm going to have then a naught cosine x plus b naught sine x. All right, and that just corresponds to the complex solution for sine x. Right, essentially, this is r equals 1 plus or minus I, and this one here is just plus or minus I in terms of the R solutions. Okay, notice that that's different from the one that I got here. So I'll start out with this first one, the a naught e to the x cosine x, b naught e to the x sine x. Okay, and how we solve these is we actually go out and we're going to plug in the trial solution into our differential equation. Now, I'm only going to set it equal to 7 e to the x cosine x. Okay, I don't need to actually set it equal to the sine x part, just the e to the x cosine x part. So that's going to be, so I'll first have y equals a naught e to the x cosine x plus b naught e to the x sine x. So y prime is going to equal a naught e to the x cosine x minus a naught e to the x sine x plus b naught e to the x sine x plus b naught e to the x cosine x. Okay, then I have y double prime. Y double prime is going to then be a naught e to the x cosine x minus a naught e to the x sine x minus a naught e to the x sine x minus a naught e to the x cosine x plus b naught e to the x sine x. So I'm right here. Sometimes I have to remind myself where I'm at. It can sometimes be a little bit jarring there or confusing, so I just have to remind myself. I've got b naught e to the x sine x plus plus b naught e to the x cosine x plus b naught e to the x cosine x minus b naught e to the x sine x. So I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. It's good. In this case, because of the nature of the solutions, we're just going to double the number of terms that we have each and every time. So that's why I'm kind of checking to make sure that all my work is right. So now what I need to do is I basically need to set up a system of equations in order to solve this. Okay, I'm going to put in my e to the x cosine x's and e to the x sine x's. I'm going to separate them out. So now let's look at number 5. And number 5 is going to require us to do variation of parameters because cosecant x is not actually one of the values that we can use in order to use our method of annihilators or undetermined coefficients. So we've got y double prime plus y is going to equal cosecant x. So what we're going to need to start out with is we're going to need to start out with the two solutions to our homogeneous part. Okay, so this is going to be d squared plus d squared plus 1, y equals equals 0. That's our homogeneous part. So that's r squared plus 1 equals 0. So r is going to equal plus or minus I. So that means that my homogeneous part, my yc, is going to end up equaling c1 cosine x plus c2 sine x. Okay, because that's what corresponds to e to the ix. So now I've got those two. Now what I'm going to do is I'm actually going to utilize my variation of parameters. We're going to be solving this system. We're going to be solving u1 prime cosine x plus u2 prime sine x equals 0. And then we'll take our derivative, right, negative sine x, u1 prime negative sine x plus u2 prime cosine x, and that's going to end up equaling cosecant x. Okay? Now, what you'll notice is that this thing here, that ends up being the Wronskian for our functions. So the Wronskian of cosine x, sine x, okay, or those are going to be the functions for the Wronskian, is going to end up being the determinant, okay, of cosine x, sine x, negative sine x, cosine x. All right, and so that's going to end up being cosine squared x plus sine squared x, and that equals 1. Now, what we'll do is we'll use Kramer's, and we're going to use Kramer's in order to solve this particular system. So remember in Kramer's, we've got u1 prime is going to end up equaling, and this is going to be 0 cosecant x, and then we'll have sine x, because we're going to replace the first column with 0 cosecant x, these two values, and the second column with sine x cosine x. So we've got sine x cosine x. We'll divide that through by the Wronskian, which is, in our case, just equal to 1. And so what we end up with is we end up with negative cosecant x sine x over 1. And that ends up just equaling negative 1 over 1, which is negative 1, right? Because cosecant x is 1 over sine x times sine x. That's equal to 1. u2 prime is going to end up equaling, now, we'll keep the first column, cosine x, negative sine x, and then we'll have 0 cosecant x, and this is going to then equal over 1 again, and this is going to end up equaling cosine x times 1 over sine x. That's my cosecant x divided by 1, so that's cosine x over sine x, and that equals tan x. Excuse me, that's actually cotangent x, not tangent x, but cotangent x. So now I need to find u1 and u2. So u1 is going to end up equaling the integral of negative 1 dx, which just equals negative x dx, negative x. And then u2 is going to equal the integral of cotangent x dx, which equals the natural log of sine x. So that's u1 and that's u2. So what that gives me then is that is going to end up giving me the solution to my my system. So my yp is going to be u1 and times cosine x plus u2 times sine x. So that's my yp. So yp ends up equaling negative x cosine x plus sine x natural log of sine x. Put everything together, we get that y is going to equal yc plus yp. So that equals c1 cosine x plus c2 sine x minus x cosine x plus sine x natural log of sine x. So this actually demonstrates our method of variation of parameters. Okay, sorry, I'll give you a moment here. So essentially what we're going to need to do is either be given the particular solutions that we're looking for, or, given the solutions to the homogeneous part that we're looking for, or we can find them if we know that we have constant coefficients for that particular equation, right? So that's where we started, right? Starting out with the solution to the homogeneous part right here. And then what we did is, I set this up. You don't actually have to. You just need to know that this is going to end up being the system that you're going to be solving, right? So our u1 prime is going to replace the first vector, okay, with, in this case, 0 cosecant x, second one with sine x cosine x, okay? And then we'll divide that through by the Wronskian, right? Figure that one out. That's going to give you u1 prime. Do the same thing for u2 prime, except we're going to be replacing the second column, okay, with 0 cosecant x, or in this case, with our set of solutions, or our right-hand vector. And we got then cotangent x. Then I have to go in and integrate. Then I'm going to take, my particular solution is then going to be of the form u1 times cosine x plus u2 times sine x. Okay, that's going to be the solution. And so my particular in this case is negative x cosine x plus sine x natural log of sine x. By the way, these are the solutions to my homogeneous part. They happen to be cosine x and sine x in this case. So I just want to be very careful. It's not always cosine x and sine x. Sometimes, you know, it just depends upon what the actual system solutions are. Excuse me, what the actual solutions to the homogeneous part actually are. So we do that, and then finally, like we've done every other time, we're going to go in and add the complementary part to the particular part, and that finishes our solution. So in order to keep all my information straight, I'm going to rewrite my differential equation. I've got y double prime minus 2y prime plus 5y is going to equal 7 e to the x cosine x. And then the solution method that I choose, just to keep myself organized, is I'm going to have an e to the x cosine x part and an e to the x sine x part. And that's because those are essentially the terms. They're like my variables for my terms. What I do generally is I just put for every different kind of term, right, that is in front of or or behind a coefficient, I create another term, okay? And then I'm going to create a system of equations, and I'm going to go to look to solve the system of equations. So in this case, I only have e to the x cosine x's and e to the x sine x's, okay? So I'm going to go in, and I'm going to start with my y double primes. And my y double prime, I've got 1 a naught, okay, minus a naught in terms of my cosine x's. There's my second one, cosine x. And then I have a plus b naught, and I have a plus b naught. And that's my y double prime. Now minus 2 times, and we're going to go into here, and we're going to get, there's 1 a naught. And then here's the second, that's a plus b naught. And there's that. And then we're going to get plus 5, and this is going to be 5 a naught. These two are going to cancel, so that's my 0 a naught. So this is going to end up being 2b naught minus 2a naught minus 2b naught plus 5a naught. So that's going to end up being 3a naught. Okay, so we got 3a naught, and your b naughts are going to cancel one another. That's great, and that's going to equal 7. The reason why it's going to end up equaling 7 is notice that we've got on the right-hand side, we have 7 e to the x cosine x. So all of our e to the x cosine x terms should equal this 7 e to the x cosine x. So there it is, there it's equal to 7. That means that a naught is equal to 7/3. Now I'm going to do my e to the x sine x, and you have seen some examples where this has disappeared. That's not going to be the case here, or it may or may not be the case. Sometimes that happens, sometimes it doesn't. I shouldn't say that it's not going to be the case here. So we've got to actually go in and do that. So we start out with my y double prime. So that gives me a negative a naught, and then a minus a naught again, and then plus b naught, because that's my b naught sine x, okay, and then minus b naught. So there's my y double prime. And then this is going to be minus 2, and then this is going to be 2 times negative a naught plus b naught. There's my other e to the x sine x. And then plus 5 and b naught. So this ends up equaling now, that's negative 2 a naught. This is going to cancel out, that becomes a 0, plus 2a naught minus 2b naught, right, plus 5b naught. And so what I get now, the a naughts are going to cancel, so I get 3b naught is equal to, and now notice that there's no, I got plus 0 e to the x sine x, right? So this is going to end up equaling 0, so b naught does end up equaling 0 in this case. So my first particular solution, we'll call this yp1, is going to end up equaling 7/3, and notice it's going to be 7/3 e to the x cosine x. The b naught is 0, so the e to the x sine x goes away. We don't have to worry about that anymore. So that's the first half to my solution. Now I want to do the second half to my solution, which is has my a naught, my b naught, a naught cosine x plus b naught sine x. Okay? And so I'm going to let that be now my y. So I'm going to have y equals a naught cosine x plus b naught sine x. And this is my differential equation, except for the fact that it's going to then have, instead, it'll have just 1 sine x. So the coefficient there is going to be 1 sine x. So I have y equals a naught cosine x plus b naught sine x. Y prime is going to then equal negative a naught sine x plus b naught cosine x. And y double prime is then going to be negative a naught cosine x minus b naught sine x. I'm now going to plug it into the system. We're going to do this with sine x's and cosine x's. We'll just put those together. So with my sine x's, I've got a negative b naught, and then minus 2 times negative a naught plus 5 times b naught. And that's going to end up equaling 1. Because remember that our system was equal to, we had it equal to a 1 sine x there. So that equals 1 for my sine x's. And now my cosine x's, I'm going to start here. I'm going to get negative a naught minus 2 times b naught plus 5 times a naught, and that's going to equal 0. So this then gives me 2a naught plus 4b naught equals 1, and then 4a naught minus 2b naught equals 0. And so now what I need to do is I need to solve that system. So I've got a system. It's going to be 2, 4, 1, 4, negative 2, 0. When I solve this system, what I get is I get that a naught equals 1/10 and b naught equals 1/5. Just using some technology there. So consequently, my solution, call it yp2 now, is equal to 1/10 cosine x plus 1/5 sine x. So what I'm going to do then is I'm going to combine that with my homogeneous part, my yc. So remember that y, my actual solution, is going to be yc plus yp, which in our case is going to be yc plus yp1 plus yp2. Okay, my particular solutions. So that's going to end up equaling, go back to C1, that's C1 e to the x cosine 2x plus C2 e to the 2x, e to the x sine 2x. So that's going to be y equals C1 e to the x cosine 2x plus C2 e to the x sine 2x plus, we'll have the first part yp1, which remember was 7/3 e to the x cosine x plus 7/3 e to the x cosine x plus 1/10 cosine x plus 1/5 sine x. And there is the complete solution to our non-homogeneous differential equation using the method of undetermined coefficients or annihilators. So, couple big pieces here. One, you don't, for my testing purposes, you don't have to use an annihilator. If the annihilator helps, great. If you want to use trial solutions, you can also use trial solutions. And I just find that trial solutions are easier to use for me, okay, than an annihilator. What I do first is I solve my my homogeneous part, and then I compare my homogeneous part to my non-homogeneous part to see if the if we actually have any kind of overlap there, right? Whether or not I need to modify my solutions. Since the two do not match, e to the x cosine 2x and e to the x cosine x do not match, I don't need to actually modify. So I'm just going to utilize the standard trial solution there. And because I have two parts to this non-homogeneous part, I'm going to have my two trial solutions. Okay? I'll do each one of them individually. I'll do them separately. Okay? Right? Using the method of undetermined coefficients. Find my coefficients for yp1, for yp2. Okay? And then I just put them all together at the end. YC, my complementary solution, plus my particular part. Put them all together, and there we go. All right, let's determine the motion of a spring mass system governed by a given initial value problem. And we're going to determine whether or not the motion is underdamped, critically damped, or overdamped. So I've got 4d squared y dt squared plus 12 dy dt plus 5y equals 0. And then I've given initial conditions that y of 0 equals 1 and dy dt of 0 equals negative 3. Okay, so my job here is to actually figure out the position of the spring mass system at time t. That's position is given by this differential equation along with its initial conditions. So essentially what this is asking me to do is to solve the differential equation. This one happens to be homogeneous, which is actually kind of nice. It's going to be not too terrible in order for us to solve. So what I'm going to do is I'm going to go and I'm going to solve it. There it is. So I got 4, and I'm going to rewrite this as y double prime plus 12y plus 5y equals 0. Okay. And so this then is going to be 4r squared plus 12r plus 5r equals 0. Okay. And now what I'm going to do is I'm going to go in and I'm going to figure out what r is, just like I normally would. Okay. And that's going to help me determine if this is underdamped, critically damped, or an overdamped system. So r is going to equal negative 12 plus or minus the square root, and this is going to be 12 squared minus 4 times 5 all over 2 times 4. So this is going to end up being then negative 12 plus or minus the square root, and this is going to be 144 minus 80 over 8. So this will end up being then negative 12 plus or minus, and this is going to be 64. So this is going to be plus or minus 8 over 8. And thus this is going to end up equaling either negative 4 over 8, or it'll end up being negative 20 over 8. So negative 1/2 or negative 2.5, so negative 5/2. Okay, and those are our solutions. Notice I've got two real solutions to the auxiliary polynomial. If I have two real solutions to the auxiliary polynomial, that actually tells me that this system is overdamped. Oh, two real unique solutions, I should say. That says that this system is overdamped. If on the other hand I had two repeated solutions, that is that if this was a squared, or if my discriminant right there was equal to 0, okay? So two repeated solutions, I would have a system that's critically damped. Meaning basically that when you pull this, the system, it would pop back, right? Maybe overshoot the equilibrium by just a little bit, but then it would snap back to the equilibrium. It wouldn't actually bounce around. This overdamped system is what it's going to do is when you pull it, it's going to move back past the equilibrium solution, then it'll pass the equilibrium solution again, and maybe it'll do more than one time. So a critically damped system is going to actually just pass that equilibrium solution just once. The overdamped system might do it several times. And then if we, on the other hand, have complex solutions to the auxiliary polynomial, what we have is we have an underdamped system. And so that makes that underdamped. Okay? In this case, I've got two real solutions. And so I have an overdamped system. My overdamped system, by the way, has a solution of y equals c1e to the negative 1/2 t plus c2e to the negative 5/2 t. And so now that sets me up for my general solution. Now I can use my initial conditions in order to figure out what my entire particular solution is. So I now have y prime is going to equal negative 1/2 c1e to the negative 1/2 t minus 5/2 c2e to the negative 5/2 t. I plug in 0, so y of 0 is going to equal c1 plus c2. And we know that that's going to equal 1 by my initial conditions. And then y prime of 0 is going to equal then negative 1/2 c1 minus 5/2 c2, and that'll equal negative 3. So what we'll have now is we'll have a system 1, 1, 1, negative 1/2, negative 5/2, negative 3. Okay, just based upon this information here and what I got for my general solution. So now I'm going to use a little technology in order to solve this. And when I solve it, what I end up with is I end up with C1 equals negative 1/4 and C2 equals 5/4. So the motion of the system is governed by the equation y of t equals negative 1/4 e to the negative 1/2 t plus 5/4 e to the negative 5/2 t. And that's what governs the system. So there you go. I mean, essentially, answering the question, determining the motion is basically finding the equation that tells me where the position is at time t. Okay, and we can, in fact, if you wanted to, you could go graph this. You could graph this one as well. And then to determine whether or not the system's underdamped, critically damped, or overdamped, take a look at the solutions to your auxiliary polynomial. If you have two unique real solutions, it's overdamped. If you have two repeated solutions, it's critically damped. And if you have two complex solutions, it's underdamped. So now we're going to go start working on systems of differential equations. And so I'm going to look at number 13 here. And we want to solve this initial value problem. Ax equals x prime, x of 0 equals x naught. And so essentially what we're going to do is we're going to go find the eigenvectors and eigenvalues in order to solve the homogeneous part. And then if we happen to have a defective system, we're going to have to actually utilize our methods for finding the additional vector for the additional vector solution for the system. So, and then when we're done with that, we're going to go in, plug in x naught, and we're going to go figure out what x naught actually is, okay? So, let's first start out and we'll say, okay, so I found the eigenvectors and eigenvalues for A, all right? And I got lambda equals 0, was the first one, and it's got a multiplicity of 2, m equals 2, and it has an associated eigenvector v1 equal to 2, 0, 1, okay? So that's its eigenvector. And then I had lambda 2 is equal to negative 1, and it's got an associated eigenvector v2 equal to 9, negative 1, 2. Okay? Now, a couple things. One is to notice that this matrix is defective. The coefficient matrix here is defective, and so consequently, I'm going to need to find another vector, right, in order to give me my three solutions. Right, it's a 3 by 3 system. I'm going to end up needing three solutions in order to actually solve this system completely. I only have 2 right now, right, which are the 2 that are going to correspond to these eigenvalues. Okay, so what I'm going to need to do is I'm actually going to need to go in and I'm going to need to go solve for the last one. Okay, and that's what we're going to do. That's exactly what we're going to do. First, we need to choose the right eigenvalue to develop that last eigenvector off of, and that is going to end up being lambda 1 equals 0. We use lambda 1 equals 0 because it's the one that's missing the eigenvector. Notice it has the multiplicity of 2, okay, but only the one vector, so we need to get another vector there. All right? Now, if you remember, well, actually, let's review a little bit about the process that we're going to use in order to do this. So we're going to need that a minus lambda I squared v1 is going to equal 0. And then I'm going to have a minus lambda I v1 cannot equal 0. We'll talk about that in just a second, the 0 vector. And then a minus lambda I v1 is then going to equal my v naught. All right, because I just need the single one, so that's the process that I'm going to use here. All right, we're going to need those three things. Once we have those, then my solution is going to end up being x1 of t is going to equal e to the lambda t times v1 plus tv naught. And there we go. So, first, I'm actually just going to write down the ones that I'm going to have. I'm going to call it an x naught is going to equal e to the 0t, okay, times 2, 0, 1. So it's actually just going to end up equaling the vector 2, 0, 1. We'll put forth a constant in front of it in just a moment. And then we'll call this x2. x2 is going to be the one for negative 1, so it's going to be e to the negative t times 9, negative 1, 2. And so that's x2 of t. So those are the other two, x naught of t and x2 of t. Now let's go find x1, the one that goes with lambda 1 equals 0. A minus lambda 1 squared. So this is actually a minus 0i squared, which just is equal to a squared. Okay, so we're just going to square a. When I square a, okay, and a is this matrix right here, it's going to end up being 0, negative 9, 0, 0, 1, 0, 0, negative 2, 0. So that's my matrix. And now what I'm going to look at is I'm going to say, okay, well, I need a squared v1 to equal 0. So I need to find a vector, v1, that's going to make this equal to 0. So what I'll do is I'll say, okay, I need to find then, basically I'm going to need the null space of a squared in this case. The null space of a squared. And so I'm going to first find my RREF of a squared. And that ends up equaling 0, 1, 0, 0, 0, 0, 0, 0, 0. And then I'm going to rewrite that so that I can figure out what my null space is. So that means x1 is free, call that t. x2 is going to equal 0, and x3 is going to equal a free variable as well. So essentially what we're going to be looking at is we're going to be looking at any linear combination of 1, 0, 0, or 1, 0, 0 t plus 0, 0, 1 s. Okay, so as long as we actually have a 0 in for the second term, we're going to get something that's in the null space of a squared in this case. Okay, so I'm going to pick one of them. I'm actually going to pick 1, 0, 0, and I'm going to make sure that the one that I choose is not actually going to give me 0 when I multiply it by a, right? And that means that it's not actually going to be an eigenvector corresponding to 0. So I just don't want 2, 0, 1. I don't want anything that's a linear, a multiple of 2, 0, 1. And so I'll pick 1, 0, 0 because that's really easy. So I'm going to just take 1, 0, 0. That's going to be when t equals 1 and s equals 0. Okay? So when I plug that in, what I'm going to do then is I'm going to go and I'm going to cut it back here. Pardon me. What this means is that my choice for v1 is going to equal 1, 0, 0. Okay, pick 1, 0, 0. All right, and I know that that's true. I know that this is true. So now I've just got to do this last part here, which is I'm going to multiply A times 1, 0, 0, and that's going to give me V naught. Okay, so I'm going to take this thing right here. Multiply it by 1, 0, 0. And what I end up getting is I end up getting negative 2, 0, negative 1. And that is V naught. So I'm just using these constraint equations in order to find first V1, all right, and then V naught. Then I'm going to plug that in for x1 of t. So x1 of t then is going to equal, remember lambda was 0, so this is going to be e to the 0 t, so that's just is what it is. So this is going to be then 1, 0, 0, e to the 0 t by this 1, that's what I meant to say, plus t times negative 2, 0, negative 1. And there we go, and we're done. And that's our x1 of t. So in this case, lambda was 0. That actually is really an important part. In other cases, if lambda is not equal to 0, you're actually going to have to subtract that other number from the diagonal. Remember, that's what you're doing, subtracting from the diagonal, right? Then you'll square that matrix and find its null space. Or if you know you have to find more than one, you might have to cube it, find the null space. Whatever you need to do, okay? There's a whole process, right, in order to like solve these systems for with defective matrices, right? Depending upon the number of vectors that you need to get back. In this case, we only have the 1. So I got a minus lambda I squared v1. That's equal to 0. Did that, found the null space. Then I made sure that it wasn't 2, 0, 1 or any linear combination of 2, 0, 1, which would have actually given it back to 0, right? You can in fact go check, although I already did. And in fact, the checking is this thing right down here, where I got negative 2, I took my matrix times 1, 0, 0, and I didn't get 0, so we're good. And that's my V naught. Then I just plug it back into the equation for x1 of t, and I'm done with finding the third vector. Finally, my solution, x of t, that's my solution, is going to equal, so we've got e to the 0 t, and it's just going to have a corresponding vector of 2, 0, 1. So I've got 2, 0, 1 plus, excuse me, that's going to be C1 times 2, 0, 1 plus C2 times 1, 0, 0 plus T times negative 2, 0, negative 1 plus, and then we'll have C3 e to the negative t times 9, negative 1, 2. That's the third piece. Okay, got 9, negative 1, 2. Great. Now all I got to do is I've got to go in and figure out what those coefficients are. So this is x naught equals negative 2, 1, 1. So I got x naught now is equal to negative 2, 1, 1. So essentially what this is saying, right, is I'm going to get, when I plug in 0, all right, I'm going to plug in 0 for t. Okay, when I plug in 0 for t, what do I get back? So let me take a look here. I'm going to get C1, right, times 2, 0, 1. There's no t even in that piece, so there it is. Plus, and this is going to be C2, and this is the t, if we set it equal to 0, is going to 0 out this vector, and we're going to get C2 times 1, 0, 0. Plus, and then C3, this is going to be e to the 0, so it's going to be 1 plus C3, and this is 9, negative 1, 2. And that we want equal to now negative 2, 1, 1. Now if you remember, this is a form we're basically looking for a linear combination, so we can utilize systems in order to solve for C1, C2, and C3. So we're going to generate an augmented matrix, 2, 0, 1, 1, 0, 0, 9, negative 1, 2, augmented with negative 2, 1, 1. And then I'm going to, go solve. And so when I solve the system, what I end up getting is I get 1, 0, 0, 3, 3, 0, 0, 1, 1, 0, 0, 1, negative 1. So I get C1 equals 3, C2 equals 1, and C3 equals negative 1. Now I can plug that back into my solution to give me my particular solution. So I'm going to get x of t is going to equal 3 times 201 plus 1 times 100 plus t times negative 201 plus, or rather minus, e to the negative t 9 negative 1 2. Now we're actually in a kind of an interesting position here because we can in fact combine some terms. So this is going to end up equaling, right, 603 plus 1, right? We can just add those two vectors together. So this is going to end up being 703 plus t times negative 201 minus e to the negative t 9 negative 1 2. And that in fact is the solution to my system of differential equations. So what we've demonstrated inside of this section is we've demonstrated how it is that we go about, one is if it was non-defective, you would just go in and plug in the values, right? You plug in the values for your eigenvectors and our eigenvalues and our eigenvectors. They all look of this form. Okay, those are the ones where we actually have eigenvalues and eigenvectors. And if we need to actually go out and find an eigenvector, this is the method that we're going to be utilizing in order to find that eigenvector, right? We have a defective matrix, so we're going to have to find the eigenvector. Finally, how I'm going to go out and utilize my initial conditions is I'm going to go and I'm going to generate a linear combination of my vectors. Okay, and then I'm going to solve for C1 and C2 and C3 using a system of equations. All right. In this case, we kind of have a special case where we can actually combine some terms. We'll always pretty much have some cases where we can combine some terms, but this is one of those ones where we can do that. So if you can combine your like vectors, go ahead and do that. But in this case, that completes our solution. Now you may also see this written somewhat like this as 7 minus 2t minus 9e to the negative t. And then this is 0, 0, so this is ending up being e to the negative t. And this will be 3 plus t minus 2e to the negative t. This is another way that you could actually rewrite that as well. All right? So that finishes up this particular problem. So now what we're going to do is we're going to find the general solution to the system, x prime equals ax plus b. What we ought to notice is that this system actually is not homogeneous. So we're going to utilize variation of parameters, which is the only method that we've gotten so far inside of this course. So what I'm going to do first, or what I need to do first in order to use variation of parameters, is that I'm going to have to go in and I'm going to have to find my eigenvectors and eigenvalues. I'm going to have to actually solve the non-homogeneous part. Okay, so we start out with solving ax equals x prime. Method for that is exactly the same as we've been doing thus far. Because we have a constant coefficient matrix. So I'm going to go find my eigenvectors and eigenvalues. I get lambda 1 equals negative 5. And so that's going to be then v1 equal to negative 1, negative 2, 3. Then I have lambda 2 is going to equal negative 2. V2 is going to equal 0, 1, 2. And then lambda 3 is going to equal 2. And it's got a V3 equal to 4, 1, 2. So those are our three sets of eigenvalues and eigenvectors. We've got three eigenvectors. So this, to go along with our 3 by 3 matrix. And so this matrix is non-defective. Great. So that gives me my general solution, called xc of t, is going to equal c1 e to the negative 5t, negative 1, negative 2, 3. plus C2 e to the negative 2t times 0, 1, 2 plus C3 e to the 2t times 4, 1, 2. And there's my system. What I need to generate now is I actually need to generate my fundamental matrix. So my fundamental matrix is going to look like this. Okay, it's big X of t. That's not a little x of t. That's big X of t. And it's going to equal, we're going to start out with the top row, right? It's just going to correspond to these three solutions. So it's going to be negative e to the negative 5t. The second row is going to be, well, it's 0, so it just zeroes out, so it's a 0. And then we have 4e to the 2t. Then next up, we've got negative 2e to the negative 5t. We've got e to the negative 2t and e to the 2t. And then we have 3e to the negative 5t, 2e to the negative 2t, and 2e to the 2t. And that is our fundamental matrix. Now recall that for our solution, okay, what we're going to need is we're going to need this fundamental matrix xu, where u is some set of equations, is going to equal xp. Okay, and that's going to be our particular part that we're going to add to our complementary part. And then we also know that xu prime is going to equal b. So we got xu prime is equal to b. So our job here is to figure out what u prime is. Then we're going to take its integral. We're going to take the integral of u prime, and that's going to end up giving me b. Okay? Or excuse me, I take the integral of u prime, it's going to give me u. I multiply that by x, and I get xp. Okay? So what I'm looking to do is I'm looking to take x, this matrix here, of t, times some vector u prime, which is unknown. This one in this case is going to be u1 prime, u2 prime, u3 prime. And that's going to then equal my b, which is t01. t01. I'm going to use Kramer's rule in order to do this. So what that means is that I'm going to first take that u1 prime is going to equal, and it'll equal the determinant of, in this case, we'll make it t01, 0 e to the negative 2t, 2e to the negative 2t, 4e to the 2t, e to the 2t, 2e to the 2t. So we've got that matrix, right, where we've taken the first column and we replaced it with our vector b. So b plus the other two, and then we're going to divide that through by the determinant of x of t. Okay? So before I do that, I'm actually going to go out and figure out what that determinant of x of t is. So my determinant, I actually utilized some technology. I found my determinant for x of t was going to end up equaling 28e to the negative 5t. Then I could actually utilize the same technology and find it here for this one as well. Okay? And when I go find that determinant, what I end up with is negative 4. So this ends up equaling negative e to the 5t over 7. So that's going to end up being u1 prime. Now u2 prime is going to equal, and what we're going to do now is we're going to keep the first column. So my first column is e to the negative 5t, negative 2e to the negative 5t, 3e to the negative 5t. Then the second column is t01. We'll replace the second column with t01 now, our b. And then we have 4e to the 2t, e to the 2t, and 2e to the 2t. And then we're going to divide that through now by the determinant of x of t. Okay, Kramer's, so that's 28 over e to the negative 5t. And when I go find its determinant, what I end up with is I end up with 7e to the negative 3t, 7te to the negative 3t, minus 7e to the negative 3t over 28e to the negative 5t. So this ends up being then te to the 2t minus e to the 2t over 4. So now we'll do u3 prime. So u3 prime is going to end up equaling, and so we've got e to the negative 5t, negative 2e to the negative 5t, 3e to the negative 5t, and our second row, our second column, excuse me, stays the same. It's going to be 0, e to the negative 2t, 2e to the negative 2t, okay? And then we'll have t0, 1, and that'll all be over the determinant of x of t, so that's 28e to the negative 5t. So that equals, so when I go in, solve that, I end up with negative 7 te to the negative 7t minus e to the negative 7t. And that's going to be all divided by 28e to the negative 5t. So this ends up being, this will be negative 1/4, negative 1/4 te to the negative 2t minus 1/28 e to the negative 2t. Okay? Not quite as clean as the other ones, but nothing too terrible either. So now I have u1 prime, u2 prime, and u3 prime. When I integrate those expressions, what I'm going to end up with now, okay, so I'm going to first take the integral of negative e to the 5t over 7, or 1/7 e to the negative 5t, and that's going to give me u1. And so that ends up equaling negative 1/35 e to the 5t. Then I'll take u2, and u2 is going to end up being 1/4 the integral te to the 2t minus 1/4 the integral e to the 2t, and that ends up equaling, I get 1/8 te to the 2t minus 3/16 e to the 2t. Right? Notice I'm not actually like putting on my my constants. The constants are into the system. We'll deal with those in a little bit. And then I'm going to take u3 is then going to be the integral. We're going to have the negative 1/4 the integral te to the negative 2t. Okay. Minus 1/28 the integral e to the negative 2t dt. Which one of these dt? Should put that all on there just to be very complete. And that equals 1/8 te to the negative 2t and this ends up equaling then 1/8 te to the negative 2t plus 9 over 112 e to the negative 2t. And that's my u3. So I got u1, I got u2, and I got u3. So now, in order to find my xp, my particular solution that I'm going to have to add to my xc, it's going to end up equaling x of t times u in this case. Okay? So we're going to take that original matrix, right, that negative e to the negative 5t, negative 2e to the negative 5t, 3e to the negative 5t, 0, e to the negative 2t, 2e to the negative 2t, 4e to the 2t, e to the 2t, and 2e to the 2t. Multiply that then by, in this case, the vector negative 1/35 e to the 5t, 1/8 te to the 2t minus 3/16 e to the 2t, 1/8 te to the negative 2t plus 9 over 112 e to the negative 2t. And we're just going to multiply those two things together. One thing to notice here, and one thing I want to emphasize, is on your exam, you absolutely are going to be able to use a computer. You can use, I'm using Symbolab here. You can use Wolfram Alpha if you want, if that's something that you feel more comfortable with, or whatever else that you need in order to do this work. So basically, you can see I'm doing the work. I've got the process. I'm just utilizing the computer in order to do all this calculation because it's a bear. It's a lot of calculation. You really want a computer to do it. When I do my multiplication, I do this multiplication, I end up equaling, right, 7t plus 10e to the 4t over 20t, okay? Or actually we can rewrite this. Let's write this as 7/20 plus 1 or e to the 4t over 2t. Second, we're going to get 5t squared minus 2t plus 5e to the 4t all over 20t. And then we'll have 5t squared minus 6t plus 5e to the 4t over 20t. Okay? And that ends up equaling xp. So the entirety of my general solution now is to add xc, right? The solution to the homogeneous part, and this xp. All right? I'm going to go up here. Have to take the advantages of computers. I'm going to copy it. Bring it down here. There we go. And we will add plus this piece right here. And there it is. That particular part looks so much larger, but it really is just another line, okay? And so this ends up being, this is the entirety of our solution. This isn't actually xc any longer. It's x. This is my xc. And this is my xp. Okay? So, to kind of recap, because there's a lot, this is pretty involved. It's an involved process. So, one, okay, we want to solve ax equals x prime. Then two, right, our x of t is going to be made up of essentially the solutions to ax equals x prime. So we call this x1, x2, so on and so forth, all the way up to xn. All right. Then 3, we'll use Kramer's to solve x of t u prime equal to b. Okay, and we're solving, in this case, solving for u1 prime, u2 prime. We've got a bunch of them, all the way up through un prime, however many we have. Will be more than 3, okay, because it just gets totally unwieldy. You might as well just write an algorithm in order to do it, to solve the system. So u1 through u1 prime through un prime. Then we integrate ui prime, right? Okay, and that'll give me ui, each one of my ui's, all right? And my ui's, right, u1 through un, right? All those different solutions there are going to end up equaling my vector u. Then I'm going to take x of t, my fundamental matrix, I'm going to multiply that by u, and that ends up equaling xp, my particular solution. Finally, my overall solution, x of t, is going to equal the complementary part. Okay, so the complementary part is this thing here. That's my xc, the solution to ax equals x prime, plus xp. And that is how we solve this non-homogeneous system using the variation of parameters. All right? It's an involved process. Utilize your computer in order to do all the calculations, or this is going to take you a long, long